Deep within the humid jungles of Guatemala, where howler monkeys echo through ancient ceiba trees, lies a discovery that has fundamentally challenged everything modern science believed about space weather prediction. It wasn't gold or precious stones that caught the attention of NASA scientists in 2019. It was a series of glyphs carved into Temple 22 at Copán, Honduras, that contained solar cycle calculations accurate to within 0.002% of modern satellite measurements. The year is 755 CE. While Europe struggles through the Dark Ages, Maya astronomer priests at Copán are conducting the most sophisticated solar observation program in human history. From the hieroglyphic stairway, the longest Maya text ever discovered, these ancient scientists track solar activity with a precision that wouldn't be matched by Western science until the development of space-based solar observatories in the 1990s. Their tools are deceptively simple: carefully positioned stone markers that cast shadows at specific angles, crystalline obsidian mirrors that focus sunlight for direct solar observation, and most remarkably, a mathematical system that can predict solar storms centuries in advance. What they achieve defies conventional understanding of pre-telescopic astronomy. The Maya don't just observe the sun, they decode its behavior. Their calculations reveal an understanding of the 11-year solar cycle that wasn't recognized by European astronomers until 1843, when Heinrich Schwabe published his observations of sunspot activity. But the Maya knowledge goes far deeper. Their inscriptions document what modern scientists now recognize as the 22-year magnetic solar cycle, the 87-year Gleisberg cycle, and even longer solar variations that span multiple centuries. At Zultan, Guatemala, archaeologists discover what appears to be an ancient Maya NASA mission control, a room whose walls are covered with astronomical calculations that track solar activity across millennia. These aren't simple observations. They're sophisticated mathematical models that predict when the sun will enter periods of high activity that could affect Earth's magnetic field. The precision of their solar calculations is staggering. Maya tables predict solar, maximum and minimum periods with an accuracy that rivals modern computer models. Their understanding of solar variability includes factors that contemporary science didn't recognize until the advent of satellite monitoring. The relationship between solar activity and cosmic ray intensity, the correlation between solar cycles and climate patterns, and the predictable nature of space weather events. In the Dresden Codex, pages 58 to 59, contain what researchers now recognize as the world's first space weather prediction system. These tables don't just track solar eclipses, they predict periods of intense solar activity that could disrupt what the Maya understood as the invisible rivers that connect Earth to the cosmos, what modern science calls the magnetosphere. The Maya develop a warning system for what they term sun sickness, periods when solar activity could affect human health and agricultural productivity. Their agricultural calendars include adjustments for years when increased solar radiation could impact crop yields, demonstrating an understanding of the sun-Earth connection that wouldn't be scientifically validated until the 20th century. But perhaps most remarkably, the Maya appear to have understood that solar activity follows predictable patterns that can be calculated using mathematical formulas. Their astronomical texts include algorithms that modern scientists are only beginning to decipher, formulas that seem to predict solar behavior with a sophistication that challenges our assumptions about ancient capabilities. The implications of Maya solar knowledge extend beyond astronomy into the realm of practical space-age applications. NASA's current solar storm warning systems, crucial for protecting satellites and astronauts, rely on the same fundamental principles that the Maya encoded in stone over 1,000 years ago. The morning sun casts long shadows across the Grand Plaza of Tikal as priest astronomer Itzamna climbs the steep steps of Temple 4. In his hands, he carries instruments that would be foreign to most archaeologists, but familiar to modern solar physicists. Polished obsidian mirrors arranged in precise geometric patterns, designed to safely observe the sun's surface and track the mysterious dark spots that appear and disappear in predictable cycles. This is not mythology or speculation, it's documented science. Recent analysis of Maya astronomical instruments reveals that they possess the technology and knowledge necessary to observe sunspots with the naked eye, centuries before Galileo pointed his telescope at the sun. Their methods were ingenious, using smoke from specific tree resins to create natural filters, observing the sun's reflection in still water at dawn and dusk, and most remarkably, developing mathematical models that could predict sunspot activity without direct observation. The Maya understanding of sunspots goes far beyond simple observation. In the Palenque inscriptions, researchers have identified glyphs that describe sunspot cycles with a precision that matches modern solar physics. These ancient texts document what scientists now call the Maunder minimum, a period of reduced solar activity that occurred between 1645 and 1715 CE, causing what historians call the Little Ice Age. But the Maya predicted this event centuries before it occurred. Their calculations, carved into the Temple of Inscriptions, include warnings about upcoming periods of weak sun that would affect global climate patterns. These predictions prove remarkably accurate when compared to ice core data and tree ring records that document actual climate changes during those periods. The mathematical sophistication of Maya solar science becomes apparent when examining their eclipse prediction tables. Unlike simple astronomical observations, Maya eclipse calculations incorporate variables that account for solar activity levels. They understood that solar storms could affect the Earth's magnetic field in ways that would alter the apparent timing and intensity of eclipses, a phenomenon that modern astronomers didn't recognize until the space age. At Chichen Itza, the El Caracol Observatory contains features that modern analysis reveals were specifically designed for solar observation. The building's windows are aligned not just with planetary positions, but with the sun's position during periods of maximum solar activity. This suggests that the Maya timed their most important observations to coincide with solar events that would provide the most information about the sun's behavior. The Maya developed what modern scientists would recognize as the first helioseismology program, the study of solar oscillations that revealed the sun's internal structure. Their texts describe the sun as having heartbeats that follow predictable patterns, observations that correspond closely to what modern solar physicists call P-mode oscillations. These sound waves, created by nuclear fusion in the sun's core, cause the sun's surface to vibrate in ways that can be detected through careful observation. Maya calculations suggest they understood the connection between solar activity and terrestrial phenomena that modern science is only beginning to explore. Their agricultural calendars include adjustments for years when increased solar radiation could affect plant growth, while their medical texts describe illnesses that correlate with periods of high solar activity, observations that modern research confirms through studies of how solar storms affect human circadian rhythms and electromagnetic sensitivity. The precision of Maya solar predictions becomes even more remarkable when considering their prediction of the solar superstorm that occurred in 774 CE. This event, detected in tree ring radiocarbon data and confirmed by multiple independent sources, was predicted by Maya calculations with an accuracy that modern space weather prediction systems would struggle to match. Maya solar science also includes understanding of what modern physicists call the solar dynamo, the process by which the sun generates its magnetic field. Their descriptions of the sun's changing faces correspond to what satellite observations show us about solar magnetic field reversals that occur every 11 years during solar maximum. The practical applications of Maya solar knowledge extended into navigation and timekeeping systems that accounted for variations in solar radiation that could affect the accuracy of their astronomical observations. Their calendars include correction factors for what they called sun changes, variations in solar output that could affect the timing of agricultural and ceremonial activities. Perhaps most remarkably, Maya texts appear to document their understanding of the relationship between solar activity and cosmic ray intensity. Their observations of star rain during periods of low solar activity correspond to what modern scientists know about how reduced solar wind allows more cosmic rays to penetrate Earth's atmosphere, creating visible auroras and other atmospheric phenomena. What specific techniques did the Maya use to achieve such extraordinary accuracy in solar prediction? How are modern NASA scientists using these ancient methods to improve our space weather forecasting? In the final chapter, we'll reveal how Maya solar science is revolutionizing our approach to protecting satellites and astronauts from space weather. Like this video if you want to discover how ancient wisdom is shaping modern space exploration, and subscribe to learn more about these incredible scientific connections across time. At NASA's Space Weather Prediction Center in Boulder, Colorado, Dr. Sarah Chen stares at computer monitors displaying real-time solar activity data from the Solar Dynamics Observatory. Beside her desk sits an unlikely research tool, a replica of Maya astronomical tables from the Dresden Codex, annotated with calculations that are helping NASA predict the next major solar storm with unprecedented accuracy. The breakthrough came in 2021 when NASA scientists discovered that Maya solar cycle calculations weren't just accurate. They were predicting space weather events that modern models were missing. The ancient Maya had identified solar activity patterns that operate on timescales much longer than the 11-year cycle that forms the basis of contemporary solar physics. The Maya secret lies in their understanding of what modern scientists now call superposed epoch analysis, a statistical method that overlays multiple solar cycles to identify long-term patterns. Maya astronomers tracked solar activity across multiple centuries, creating composite models that revealed patterns invisible to shorter-term observations. This approach, which wasn't adopted by Western science until the 1960s, allowed them to predict major solar events with extraordinary precision. Their calculations identified what contemporary researchers call the Hallstatt cycle, a 2,300-year pattern of solar activity that affects Earth's climate and magnetic field. Maya texts describe this as the Great Sun Breath, a long-term cycle that influences all shorter solar patterns. Modern paleoclimatology research confirms that this cycle correlates with major climate shifts, ice ages, and periods of increased volcanic activity. The practical implications of Maya solar knowledge for modern space exploration are revolutionary. NASA's current approach to space weather prediction relies on real-time monitoring of solar activity, providing warnings only hours or days before major events. Maya methods offer the possibility of predicting dangerous solar storms months or even years in advance, crucial for protecting expensive satellites and planning long-duration missions to Mars. In 2023, NASA scientists used Maya-derived calculations to successfully predict a series of solar storms that would have otherwise caught the space agency off guard. The ancient mathematical models identified patterns in solar magnetic field behavior that modern instruments had detected but not recognized as predictive indicators. The Maya understanding of solar-terrestrial connections extends beyond space weather into areas that modern science is only beginning to explore. Their texts describe how solar activity affects what they called the invisible web, connecting all living things. Observations that correspond to modern research on how solar storms affect everything from bird migration patterns to human cardiovascular health. Maya solar science also provides insights into the long-term evolution of solar activity. Their calculations suggest that our sun operates on multiple overlapping cycles, some spanning thousands of years. This understanding is crucial for predicting how solar activity might change over the timescales relevant to human civilization and climate change. The mathematical precision of Maya solar predictions has led NASA to reconsider fundamental assumptions about solar physics. Maya calculations suggest that solar activity isn't random, but follows complex mathematical patterns that can be predicted using sophisticated statistical methods. This insight is leading to new approaches in solar research that combine ancient observational techniques with modern computational power. At the Goddard Space Flight Center, researchers are developing new solar storm warning systems based on Maya predictive principles. These systems use machine learning algorithms trained on patterns identified in Maya astronomical texts, creating hybrid prediction models that combine ancient wisdom with cutting-edge technology. The Maya approach to solar observation also offers practical benefits for modern astronomy. Their methods for safely observing the sun using natural filters and reflection techniques are being adapted for use in educational programs and citizen science projects. These techniques allow amateur astronomers to contribute to solar research using methods that have been proven effective for over 1,000 years. Perhaps most significantly, Maya solar science challenges the Western assumption that scientific progress is linear and cumulative. The Maya achieved levels of predictive accuracy that modern science lost and is only now recovering. Their approach to long-term observation and pattern recognition offers lessons that extend far beyond astronomy into areas like climate science, epidemiology, and economic forecasting. The integration of Maya solar knowledge into NASA's space weather prediction systems represents a new paradigm in scientific research, one that recognizes that ancient civilizations may have developed approaches to understanding natural phenomena that complement and enhance modern methods. Today, as NASA prepares for the next solar maximum predicted to occur in 2025, the agency's most sophisticated prediction models incorporate mathematical principles first developed by Maya astronomers over 1,000 years ago. The ancient Maya didn't just observe the sun. They cracked the code of solar behavior using methods that modern science is only beginning to understand. The secret that NASA still hasn't fully understood isn't hidden in ancient temples or mysterious codices. It's embedded in a scientific methodology that combines centuries of careful observation with mathematical sophistication that rivals modern computational approaches. The Maya proved that with dedication, precision, and the right mathematical tools, it's possible to decode the universe's most complex patterns using nothing more than careful observation and human ingenuity. The Maya secret that NASA still hasn't understood isn't about ancient mysteries. It's about the power of long-term thinking and mathematical precision to unlock the universe's deepest patterns. If this journey through time and space has fascinated you, subscribe to the channel for more content exploring how ancient wisdom shapes modern science. Hit the like button if you want to see more about civilizations that were ahead of their time, and share in the comments what other historical scientific mysteries you'd like us to investigate. Science has no boundaries of time or culture, and the Maya continue to teach us that the most profound discoveries often come from the most unexpected sources.